Let's start at the beginning. Those of us following along in Young and Friedman, this is chapter 31. If you're following along in Six Ideas, you might be missing this content. I couldn't find it, which I find interesting. And those folks following along in another text, like OpenStax or something, you're looking for a chapter about alternating current. That last bullet point is useful. There's a particular example I declared a while back that I wanted to examine, but I think it's better having talked about alternating current in the first place. So at the end, when we talk about transformers and why they are a good thing, why we would want to use them in the first place, we'll return to an example from DC circuits chapter. You know, if you're following along in the textbook, it's the chapter on DC circuits that talked about this, to discuss transmission voltage from the power grid. How is it that a radio tunes to a particular station? And if we are going to use an alternating current source, how do our different components behave? Is a capacitor going to have the same response, pardon me, for all driving frequencies, for all source frequencies? Or would a capacitor prefer very fast alternating current or very slow? And what about an inductor? I suppose a resistor doesn't much care. It's going to dissipate power according to the current running through it. So that's the resistor doesn't really get a choice. But the capacitor and the inductor, I think we expect some sort of preference. The faster we try to alternate the current, for example, the more the induction associated with the coil of the inductor matters, because the more rapidly we change the current, in other words, the greater is di dt, the greater the induced EMF in the inductor that opposes the current we're trying to change. So the faster we try to alternate, this is I'm just spitballing, the faster we try to alternate a current passing through a circuit like we looked at, the worse a time we're going to have pushing that current through the inductor as we change it and change it and change it and change it. The inductor is going to all the time resist those changes. I'm pondering what a capacitor would do. How do I expect it to respond to different frequencies of alternating current? The electrical grid, the power grid, supplies power in the form of electricity, moving charge, to our offices, dwellings, and so on, almost always by AC current anymore. And that's the reason for the charging brick that goes with every single device you've got. Its job is to convert from AC delivery current to DC battery charging current. If as soon as we get a battery involved, we start talking about DC. Battery, just a storage device, doesn't really, capacitor doesn't really want to talk about AC current. It wants to get, a consistent voltage so that it charges up to that voltage. A sinusoidal voltage. We could use a lowercase v for the instantaneous value as a function of time. We could use a capital V for the amplitude and some angular frequency, omega. The frequency, not the radian or angular frequency, but just the plain old frequency, cycles per second in the US and Canada, 60 hertz, 60 times every second. The polarity of the potential difference flips. And suppose we defined an alternating current the same way. If we needed to discuss the fact that these two quantities were out of phase for some reason, we could introduce a phase angle so that we were talking about, cosine of omega t plus phi, for example, which we might have to do. What is a phasor? And why do I want one? I'm so glad you asked. Not only are the inductor, the capacitor, and the resistor voltages out of phase with each other, but they have completely different amplitudes as well. These steady state solutions are sinusoidal. But the maximum, the amplitude is something like 3 volts, something like 8 volts, something like zero point 0.2 volts across the resistor. These are very different amplitude responses in addition to being out of phase. This is a lot to keep track of, especially if we have to update these graphs in real time. This is hard to parse. And it is not clear at all what the connection is between them, except maybe that the grid markings appear to be moving from right to left. Time appears to be increasing at the same rate for everybody. So these do seem to be, as this might indicate, these do seem to be parameterized by a consistent parameter, time. But apart from that, I don't see how this is related to this, is related to this, is related to that. I can sort of see phase relationships, but the amplitudes, I have no idea. How do we put 3, 8, 0.2, and 5 together in any kind of meaningful way? The answer is with a diagram of rotating vectors like this one. The amplitudes, the size of those vectors, the amplitudes are constant. The trouble with this particular animation is that I can't pause it. I can't press the button. Nope, it just continues rotating. We can see that the blue vector that represents the capacitor and the green vector that represents the inductor are, in fact, directed 180 degrees away from each other. And we can see that the resistor, red vector there, is directed perpendicular to each of them. And that if we follow them in the order 1, 2, 3, first, green, red, blue, green, red, blue, green, red, blue. So there is 90 degrees of phase between the green to red and then red to blue. So there's a total of 180 degrees of phase between green and blue, and the order is consistent. Green, red, blue. Inductor, resistor, capacitor. Is that what we observe here? 3.57 seconds. The inductor has a maximum. Somewhat after that, the resistor has a maximum. Somewhat after that, the capacitor has a maximum. At the time when the inductor has a maximum, the resistor, if it's 90 degrees, the resistor should be 0, which it is. At that same time, the capacitor should have a minimum, which it does. All right. So something about this representation is useful. We can see the alternating current. We can see the alternating potential from the source. And here again, it doesn't look like the current through the circuit and the potential difference across the source are in phase. Here, the current has a maximum, and then just a second later, the voltage gets to its maximum. And here we see the current leads the supply voltage by 60 degrees. How do we know that? Well, I guess that's this same angle here. But where did that come from? What? What the hell is Z? And what is this noise? X sub C. I mean, we're just making stuff up here. This looks like, I've seen a curve like that before, and it was in Young and Friedman back in chapter 14 when they were discussing the oscillation, the damped oscillation of a mass on a spring. And they put a graph like that, and that peak there, that peak response was resonance. So here's this button that says set resonance. So I'm thinking, and that puts us at this response. And we can see that that increased the size of all three of these vectors. Interestingly, the capacitor and the inductor now have equal voltages. Before, they did not. Or wait, yes, they did. Wait, I'm changing the wrong variable. It's interesting that changing the resistance changes not the frequency at which resonance occurs, but the size of the response. Oh. But no matter what the size of the response is from the capacitor and the inductor, the resistor is still dissipating exactly as much power as is supplied by the source. The current is what it is. We change the current, the power delivered by the source increases because same voltage. Same voltage, the voltage of the source, V sub 0. Different current, different power, but same potential difference across the resistor means the same power dissipation in the resistor. So this oscillation just serves to keep the oscillation. Like that's the oscillatory component, and here's the power delivery component. All right, cool, cool, cool. Resonance occurs when X sub L is equal to X sub C. And I guess that makes some sense. The voltages are equal at any rate. And if they are aligned in some sense, then one isn't trying to like oppose the state of the other, that they're working in concert. The inductor is trying to push current through to charge the capacitor like the capacitor wants to do. And then when the capacitor is trying to discharge, it's pushing current through the inductor like there's an alignment to their responses. Also, what is this triangle? I mean, I guess it's the angle phi. If angle phi is not 0, then there are three different triangles that could be represented by the angle phi, it seems like. This one confuses me a little bit. I'm a little bit nervous that that's supposed to be a V right there. It's a little bit weird to subtract a V minus an X. I don't know what X is, but that's a little bit odd. But I'm not sure yet what is this thing? I mean, it's a cool animation. Is there some sort of analysis that goes with it?